Hello, in this week lab, you will be working on diffraction and interference. So in this video, I'll go over the theory and also I'll show you the sample pictures of a real experiment data. So you will be seeing like diffraction and interference pattern that you would observe in a real lab setting. Anyway, you will be using a simulator. You will be able to observe same type of patterns in the simulator as well. All right, so the plan is to use a single slit and a double slit. So in the real experimental setup, what we do is we place a laser light and then we place the diffraction plate. Of course, about 1.5 meter away, we keep the screen where we can observe the diffraction patterns on the screen. So usually a diffraction plate looks like that. So it has a lot of patterns on there. That's what it labeled like A to J. So for example, at C, we have a single slit, and at D and E, we have a double slit. So each has different widths. So here in this one, plate C has a 0.16 millimeter single slit width, and then at D we have a double slit with the slit width of 0.125 millimeters. These numbers are not useful in the online lab. However, here I'm demonstrating you what would you use in a real lab setting. All right, so diffraction happens due to the wave quality of light. So, you know, light has a dual nature. Sometimes it behaves like a particle, sometimes it behaves like a wave. So when you talk about the diffraction, it's about the light behave like a wave. So here, for example, let's say you are sending a marble through a tiny opening like this one. So here this is the single slit. So the black color two borders are the have an opening over here. So that is the single slit. So if you're sending a marble or something like a particle through this one, it cannot bend and create these fringe patterns. So these fringe patterns are created because of the wave nature of the light. So if you look at a two-dimensional picture here, so we have a single slit opening and we're sending the light through it. And here we have the screen over here. So when the light passing through it, it will create this diffraction pattern. So in our real experiment, we would observe a pattern like in this picture. So we have a bright fringe at the center, and then we have other bright fringe in this pattern. So the middle one, we call this as the central maximum, and then we have the secondary maximum and likewise. And also we can observe the same pattern like symmetrical around the central axis. So if you draw a center axis, the patterns is symmetric around it. So this is exactly what you would observe in a real lab setting. And we call this central center fringe as the central maximum, where you see the highest intensity. So if we draw the intensity graph, you will see a higher intensity over here. The others have the same pattern, like a wave pattern, but the intensity also is not a maximum as this one. That is the middle center fringe. So it is receiving a high amount of light. So that's why it has a higher intensity. So we can write the theory for this diffraction. So in generally, the dark fringes occur when m lambda equal a sine theta. So here m being the order number, and then lambda is the wavelength of light you're using. So here we are using red light, so it's a wavelength of red light, and a is the size of the slit, as in this picture. So opening size of the slit is the A, and sine value of angle theta. Theta is the angle over here. So if you draw your fringe pattern, I think I can annotate on this. So let me draw over here. So if you draw the intensity graph on top of the screen, it will be something like this. So same thing happen on the other side. So here, as you notice, the xm is the height from the central maximum. This is the center of the central maximum, and this is the first minima. And we have second minima over here. On the other side, we have first minima and the second minima, right? On this picture, the fringe pattern picture over here. So this is the first minima and this is the second minima. So you might able to see it like a dark fringe on the simulator, but in real life, you will see a dip in the intensity. Anyway, so this is the first minima on the other side, and this is the second minima on the other side. So the equation for this dark fringe is m lambda equal a sine theta. Now, let me get rid of my annotation, and then, so the xm in the equation is the distance from the central maxima to each minimum, and L is the distance between the screen and the single slit. So in my slide, I use it as 1.5 meters. On the simulator, it will be a different number. Please read the instructions so you can understand what are this distance. So as you see, the length here is really comparatively really large to the xm value. You see here, this is not 1.5 meters, right? So it is a couple of millimeters. So it's compared to the distance from the slit to the screen, this is a tiny distance. So in this case, we can apply the small angle approximation where we're going to consider this angle is tiny, because when the xm is smaller, this whatever the hypotenuse will be landing onto the L, right? So this angle will be very, very small. So in the small, if you apply the small angle approximation, then the tangent value of this angle is same as the sine value of this angle. So in that case, we can write it as xm over L, because sine theta is the opposite over hypotenuse and the tangent theta is the opposite over adjacent. Here, the opposite being the xm and the adjacent is the L, and hypotenuse is the distance from here to here. So when the angle is tiny, angle is very small, then the L is same as the hypotenuse over here. So we can make this small angle approximation, and if we modify, if we apply that idea to the equation here, m lambda equal a sine theta, our equation can be modified as m lambda equal a, and instead of sine theta, we put xm over L. So we have m lambda equal a times xm over L. So that is what you see on your lab manual. So the this is for the single slit, and we are considering the minimas, and you are measuring the distance from the central maximum center to the minimas, and the equation will be the slit width equation will be m lambda L over xm as in this slide. Then let's look at the Right. So here's a sample picture of a real data. You're not going to use any of these numbers. So as you see here, this is what you would observe in a real lab. So you see the central maxima and a minima and another bright fringe. So likewise, so you're measuring the distance from the center to the first dip and the second dip likewise. All right, so when you're using double slit experiment, we call this as the Young's two slit experiment because he's the scientist who would figure it out about these patterns. And then as I mentioned earlier in the slit, you notice D and E positions. That's where we have these double slits. So in a real experiment, you would use those two slits to do the analysis. Now, as you see here in this 2D diagram, it is different from a single slit. Now we have two single slits, so it is a double slit. So in this case, we will observe both interference and the diffraction. So diffraction coming from a single slit and the interference happen from this double slit combination. So here, the same thing, you keep the double slit and then you keep the slit and then you keep the screen away about 1.5 meter away from the slit. And then when the light travel through this slit, again, due to the quality of wave quality of light, it will create these fringe patterns. So as you see here, this would be the observation for a double slit experiment. As you see, it has the same pattern that created by a single slit. So this center fringe, let me annotate on this so you know what I'm talking about. So in the central fringe on this one, you see the same pattern that you would observe with the single slit, where you have a central maxima and these other maximums and the minimas in between. So these are closely spaced fringes due to the interference of light from the two slits. And then we have widely spaced fringes due to the interference of light from the two single slits. So here, this is one envelope. So inside the envelope, you see this pattern. And then there's another envelope here, right? And also another envelope over here. So each envelope has its own interference pattern embedded into it. So if you draw the intensity graph, it would look like this. This is the intensity graph, right? So in the middle, you see this fringe pattern over here. So in the experiment, it is very clear to observe all this, but not these ones. These are very low in intensity, as you see in this graph. So it's really hard to observe, but we will be seeing the inside of this central fringe. Well, in the simulator, you would see a better picture and a clear picture. So you should be able to do all these measurements that require to do the calculation. Well, now let's talk about the theory here. In this case, when we are using the double slit setup, so the bright fringes occur in the same kind of a same equation as we use for the single slit. But remember, this is for the bright fringes. So m lambda equal d sine theta. And again, you can use the small angle approximation because the slit, the distance from the slit to the screen is larger compared to the size of the fringe size. So we can apply the small angle approximation. In that case, tangent theta and sine theta will be equal to each other, and it is xm over L. So we can modify this equation as m lambda equal dxm over L, and you can get an equation for the d, the size of the two slit over here, the slit width will be m lambda L over xm. Here I use the letter m to indicate the fringe number, and earlier with the single slit we used letter p to indicate the order number of the dark fringe. Here we are talking about the bright fringe. So this is an example of a real experimental data. So as you see here, in this equation, d being the size of this double slit, m being the fringe number, and xm is the distance from the central maxima to the center of the next maxima. So here you see the two bright fringes. Not like earlier, we are not measuring the distance to the minima, but to the center of the second fringe here. So distance from m0 to m1. That's how you would do the measurements in a real experiment. Of course, in the simulator, you will be doing same kind of measurements as well. So this is the simulator that we will be using. The link is given on the canvas and also on the lab manual. And we will be using both interference and the slit for our analysis. And I'll create another video about the experimental setup. Please watch that and start working on the lab report.